right, disclaimer that this is a live recording. Okay, so, all right, so the first thing when we're going to solve these, I like to call them mixed circuits just because they're going to have resistors in both series and parallel. You do need to know Kirchhoff's laws. Okay, so I want you to write them down, and these are pretty key for solving any of these problems. So the very first one that's up there says current into any junction must equal the current out of the junction. And I've said this a few times just in the basic stuff that we've done, but you're going to need that quite a bit in order to solve these problems correctly. The second one says the sum of the voltage drops in any loop must be equal to the total voltage of the source, meaning whatever that battery, whatever the voltage was on that battery, if I follow a path all the way around a circuit, I have to use up, I use that term kind of loosely here, you have to, all the voltage drops across every single resistor must add up to that total amount of voltage that that battery had. Okay? Okay, so another thing that we need to keep in mind as we go through these problems is that resistors that are in series share the same current, and then resistors that are in parallel will share the same voltage drop. Okay, and again, these are going to be some key ideas as we go through and solve some of these problems. Okay, now what I would do is with your Kirchhoff's rules and these two statements, have those readily available as we go through and actually try to solve the circuit. Okay, so here is an example circuit. Can you guys read those numbers fairly well? Okay, so once we have our circuit drawn out, it's important to note, okay, that we've got, if I follow the path here, and I'm going to use conventional current. So conventional current is the direction the positive charges would flow, which would be away from the positive terminal. So the current's coming up this way. You're going to notice that we reach two resistors that are in series, and then we reach a junction. Right here is a junction. So the current has choices. It can either go this way through the loop and back around, or it can go this way through the loop and around. Okay? Now, we've got some things here that are in parallel to each other. But even inside of the ones that are in parallel, we've got two other ones that are in series. So the best thing to do at this point would be to go ahead and simplify these two resistors that are in series. So if I've got a 6 ohm resistor and a 2 ohm resistor, if they're in series, they should add up to what? 8 ohms. So I put right here, and it's written in red, so it might be a little harder to see right now. 2 resistors in series, 6 plus 2 equals 8 ohms. Okay, so now what I've done is I've redrawn our situation with an 8 ohm resistor in there. Okay, so now that we've simplified the 2 resistors that were in series, we've now got one resistor here that is essentially the equivalent of those two. But now I've got 2 resistors that are in parallel. Right? So I'm going to simplify these. Now remember that when you add resistors that are in parallel, okay, you have to add the inverses. So over here in red, which again is going to be kind of hard to see maybe for some of you, I've got 1 over 8 for the 8 ohm resistor plus 1 over 4 equals 1 over the resistance, the total resistance. So down here I've got 3/8 equals 1 over R, and then I took the inverse, so I put each one to the -1. Or you could just do 8 over 3, that's going to be your resistance. So the total resistance that ends up from that one is 2.67 for the total resistance. Okay? Now, once you've actually resolved those 2 resistors into one resistor, then we go ahead and we draw another picture. Okay, so now that we've got resistors 3, 4, and 5 all reduced into one resistor, I've just got 4 resistors all in series, yes? Okay. So 4 resistors in series just becomes adding them all up. So we've got a 3, a 6, a 2.67, and a 1, which means we end up with a total of 12.67 ohms as our total resistance, which means if I drew a new picture, bam, look at that. Okay, so now that we've got our resistance, which included all resistors, 1, 2, 3, 4, 5, 6, all of them, we have the total resistance of the circuit. Now we're able to find the actual total current. And I've just listed it I with a little t at the end, actually capital T for total current. Okay, so we know the total voltage through the cell, or through the circuit, is 9 volts. Okay, and then the total resistance was 12 2/3. Okay, so then that allows us to solve for the total current, which ends up being 0.71 amps. Okay, so reminder that one of our rules was the current flowing into any junction must be the same amount of current that comes out of the junction, right? So here's what we're going to do with this information. We're going to go back. We're going to start working backwards now, back through our drawings, okay? And we're going to start finding voltage drops and currents through each resistor. Okay? So I'm going to go one step backwards. You can either redraw it or you can just go back to your previous drawing. The one that we did right before our final resistor. Okay? Okay, so now that we're back and we're starting to basically expand the circuit back out. We just managed to go all the way down and reduce it. Now we're going to go backwards. We're going to start expanding it again. So my first step, one step back on like your third note card or whatever that I had. I got the 4 resistors in series. Now keep in mind, the 3 ohm is by itself, the 6 ohm is by itself, and then resistors 3, 4, and 5 are actually are written here as one resistor, even though they're technically 3 different resistors, right? And then the 1 ohm is all by itself as well. Now, we just got done solving for the total current to be 0.71. So draw in this little arrow that is showing us the direction of the current and write that the current is 0.71. Now, one of our little rules was the current into any junction must be the current out. So then what is the current that flows through the 3 ohm resistor? 0.71. Then the current times the resistance will give you the voltage drop through that resistor. So all I've done for every single one of these resistors, because they're all in series, the 0.71 amps flows through each resistor, yes? So all I do is I take the resistance and multiply by the 0.71. That gives me the voltage drop across the 3 ohm. I do the same thing for the 6 ohm. I do the same thing for the 2.67 ohm. And I do the same thing for the 1 ohm. So the voltages that you get, 2.13 for the 3 ohm, 4.26 for the 6 ohm, 1.9 volts for the 3, 4, and 5 resistors, which had the total amount of 2.67 ohms, and 0.71 for the 1 ohm. Now, one thing that we should make note of, do all of those voltage drops add up to the total voltage of 9 volts? They should. If you've got 2.13, 4.26, 1.9, and 0.71, those ought to add up to 9. Okay? Are we good with that? Okay. So then going back, and now we're just going to look at that section that was resistors 3, 4, and 5. Okay, so now if we're just looking at the section that was originally in parallel, okay, we've got the 8 ohm resistor that was made up of the 6 and the 2 ohm resistor in series, so it's written as 4 and 5 there with the 8 ohms. And then the other one was the 4 ohm. Now, keep in mind that, again, one of our rules is that the current that flows into a junction must be the current that comes out. However, there are two different paths for the current to go. So this is a spot where the 0.71 amps doesn't just go this way and this way. The current has to split. So how exactly are we going to solve for how much goes which way? Well, the other rule is the one that comes in handy in this one, where it says the voltage drop across any loop has to be the same, or add up to the total amount of voltage throughout the circuit. So on this particular section, which was originally that 2.67 ohm resistor when we had it all together, what was the voltage drop across just that resistor? It was your 1.9 volts, which means going this way, there has to be a potential drop of 1.9 volts. Going this way, there has to be a potential drop of 1.9 volts. Therefore, what I can do is solve V equals IR for both resistors where I'm using 1.9 volts as my voltage drop. So all you got to do is use 1.9 and the 8 to solve for the current that flows this way, and then use your 1.9 and a resistance of 4 to find the current that flows this way. So what I get on the top is 0.238 amps, and what I get on the bottom here is 0.475. Now there are some rounding issues, okay, but ideally, when it's all said and done, the total current of those two currents better give me the total amount that flew or that came into the junction itself. Which, if I add up 0.238 and 0.475, it's pretty close to 0.71. All right, so once we actually have the current now for this side, this particular resistor is still made up of two other resistors, right? It's made up of the 4th and 5th resistor. So I'm going to look at now just that section because I know the amount of current, and I know that for objects in series, okay, for objects in series, that amount of current has to flow through both of these resistors. Therefore, each one of these resistors would have their own voltage drops. Okay, so knowing the current and the resistance, I can solve for the voltage drop across each one. So V equals IR, I use my 0.238 times the 6 ohms, and on the other one the 0.238 times the 2 ohms, and I end up with 1.43 volts across the 6 ohm resistor and 0.48 volts across the 2 ohm resistor. And as long as those two voltages add up to the total voltage drop that was supposed to be across it, which was 1.9 volts, then you did it right. 1.43 and 0.48 we get not quite right on, but again, there's some rounding issues there. Okay? Make sense so far? Okay? So then essentially the next card is just a summary. This gives me a summary of the total resistance, the total current, and then the voltages and currents across or through each resistor. So I've put the voltages, voltage 1, 2, 3, 4, 5, 6, and the currents 1, 2, 3, 4, 5, 6. Okay? Now, I'll put this back up in a minute, but for the purposes of the video, I just want to show you one other circuit. This is going to be the next one that we practice. Okay, we're going to do this one. I'm not going to record this one, but if you go back and you watch the video again, this can be your practice one when you're all said and done. Try to do it again. Okay?